15. Madhu is expected to take over, right?
Right, yeah. So you would like to start? Yeah, please.
I could, yeah.
Yeah,
Let me just
go
share
ahead.
my. So are you able to see my slides now?
Yeah, all good.
Okay, so let's get started again. Good morning, everyone. It's again a pleasure to be back here on a Monday morning. And with the new year starting, I think it's a good way to start off with some interesting lectures. So today we will talk about multi-threading and multi-cores, right? I'm not going to talk about a lot of things today. I'm only going to give a very quick introduction to different types of parallelism and then talk about how multi-threading and multi-cores could be used for supporting thread level and task level parallelism. So when we talk about different types of parallelisms that can be exploited, we started off these lectures with instruction level parallelism. And we talked about exploiting instruction level parallelism in superscalar processors. We also saw the architecture of the very long instruction word architectures. Not sure if EPIC was covered, which is the explicitly parallel instruction computing, which also exploits instruction level parallelism. Instruction level parallelism is a common thing, is a common theme which is going to be recurring again and again. And you will see instruction level parallelism being exploited right in all processors, including the modern processors and so on. The next level of parallelism is thread level parallelism, where individual threads are executed in parallel. And the concept of a thread is similar to the concept of the thread that you know in OS operating systems, right? Where it's actually a stream of instructions, right? And typically this, different threads share the different threads of a process. They share the process address space and so on. Let's not get into those levels of details here, but our intuitive understanding of thread is what we are referring to here as well. So when we talk about thread level parallelism, it is the parallelism which is exploited across different threads, right? And thread level parallelism can be supported either in a multi-threaded processor or in a multi-core processor. So we will see how that is going to be exploited. Thread level parallelism is also something which is happening at fine grain level. As opposed to thread level parallelism, one could talk about task level parallelism, which is at a coarse grain level, right, where different tasks, roughly, different processes, or so to say, right, interact with each other and exploit parallelism, which is what is called as task level parallelism or coarse grain parallelism. And again, task level parallelism can be exploited by multi-core processors or multi-processor systems. You have seen examples of multi-processor systems in some of the lectures in the last week. The last thing that we want to talk about in this context is the data level parallelism, where you try to exploit what is called the SIMD parallelism, single instruction multiple data. An extended form of this is the single instruction multiple threads, which is the SIMT parallelism, which is exploited in graphics processing units. In the olden days, SIMD parallelism was exploited in array processors and vector processors, whereas today modern processors support SIMD extensions like MMX instructions or AVX instructions, advanced vector extension instructions, which exploit some amount of data level parallelism. But more importantly, in this week, you will also hear more about graphic processing units, which are exploiting different forms of, which are exploiting actually data level parallelism. Okay, so that's about the different types of parallelism. In this lecture, we will focus on thread level parallelism. And as I mentioned earlier, this intuitive understanding of what a thread is really what is holding it. Basically, each thread is an independent stream of instructions, and when multiple independent streams of instructions are executed, right, because these are independent of each other, right, they could be executed in parallel, and that is where you exploit thread level parallelism. And this kind of a thread level parallelism is explicitly specified by the application. It's explicitly specified in the application It could be exposed either by the compiler or by the programmer, and it could be done using different kinds of thread libraries or parallel languages. So the notion of pthread that you might be familiar with could be used for writing these threads, right? Or one could also use parallel languages or libraries such as OpenMP, Silk, or thread building block TBB, right? And so on and so forth to write thread level parallelism or to expose thread level parallelism. These threads which can be executed in parallel could be coming from the same application, which is what we talked about, where the user exposes this parallelism, or they could be coming from different applications of the same user. For example, when a user is executing something in the background and executing something in the foreground, or for example, when you are running your Netscape browser, or when you are running your Chrome browser, right? Different tabs or different activities that are happening in parallel, multiple downloads that are happening in parallel. These are all again different threads which are in execution, which exploit some form of thread level parallelism. Right? You could also have user applications interacting with system applications and so on, and there could be these different threads which could be working in parallel. Or these threads could be from different users as well. For example, when you talk about services like the Google services, right? Google search engines, right? Where requests from different users come to the search engine, which are actually searched in parallel. And each of these requests is actually an independent thread of instructions, and they could be executed entirely in parallel. Or today, when you talk about cloud services, right? Any of these services which are executing where different users actually give their requests could be executed in parallel, and that is also some form of thread level parallelism. So again, just to summarize, the thread level parallelism can come from a single application, or can come from multiple applications of the same user, or can come from multiple users as well. So thread level parallelism is available easily, and therefore you would like to exploit it. What are the architectures to support thread level parallelism? We'll talk about support for multi-threading, okay, what is called as hardware multi-threading, which supports execution of multiple threads together. That's one form of architecture that we talk about. And in this, the design is such that, right, certain parts of the processor are actually shared across these different threads, and certain other parts of the processors are replicated. For example, things like the arithmetic and logic units, right? The execution function unit pipelines, they are actually shared across the different threads. Whereas things like processor registers or the program counters, right? They are replicated one for each thread. There are certain other resources like your caches or branch predictors or your load store queues or your reorder buffers, which are actually shared between these different threads. How exactly they are shared, what is the impact of that, we will talk about it a little later. But essentially, this is an architecture in which there is a single processor. Some parts of the processors are shared across these different threads. Some parts of the processors are replicated. This is what is called hardware multi-threading, right? As opposed to this, you can also think of multiple processors in a single chip or multiple cores in a single chip, what is also called as chip multiprocessing or multi-cores. You could also talk about multiple processors connected together in some form, which can support multi-threading, right? Or you could have a combination of the hardware multi-threading and multiprocessors together, and that also could support thread level parallelism. We will talk about both of these instances and then see how they are helpful. That is why this lecture is titled as multi-threading and multi-cores together. Okay. So with that introduction, now let's just move on to understanding multi-threading in a better way. Okay. So first of all, why do we want to talk about multi-threading? What is multi-threading? Many of us are familiar with the notion of multi-programming. right? When you studied about operating systems, you were told that when a process is doing I/O, it's actually context switch, some other process is brought in, and that starts using the processor, right? There we wanted to keep the processor resource busy, and therefore an idling process or a process which is waiting on I/O, right, has been context switched and another process has been brought in. Multi-threading is essentially the same idea applied to threads rather than the processes. And you want to address the latencies not just of I/O but other latencies which are large enough. So the idea here is essentially to tolerate the latency. And when we talk about latency, it could be a long latency memory operation or a long latency incurred by, let's say, a floating point pipeline. Or it could even be a long latency incurred on an L2 cache miss, right, which has to go to maybe L3 or a memory. Or it could be, right, a latency due to a synchronization event. Right? When any of these events happen, the processor has to stall for this event to complete. And in the time when the processor is stalling, instead of just idling or not doing anything or stalling the processor clock cycles, you could do a context switch, or the processor could do a context switch, bring in another thread and start executing its instructions, thereby not wasting the processor resources. So the first idea of multi-threading is to tolerate the latency. And by doing this and by executing other threads, we are essentially trying to improve the system throughput. Okay. You could also use multi-threading in some clever way to improve the superscalar issue width, or to fully utilize the superscalar issue width, not to improve the superscalar issue width. You already have a superscalar weight, but to effectively use that superscalar weight, you could use multi-threading. We will talk about simultaneous multi-threading, which essentially tries to achieve this. Okay. And why are we doing all these things? Why can't we just do exploit instruction level parallelism, and isn't that enough? The answer is the available instruction level parallelism in programs is quote unquote limited, right? It is limited because of the dependencies in the program. It is limited because of the available bandwidth in the hardware. For example, when you want to fetch instructions or when you want to fetch data from memory, you are constrained by the memory bandwidth and so on and so forth. And then programs do have control dependencies and branches are there everywhere in the program. We do have good amount of branch prediction, but still branch prediction accuracy is not 100%. It's probably 95% or 97%, right? So they also limit the amount of instruction level parallelism which is available in the program. Therefore, to go beyond this instruction level parallelism, we need to have other mechanisms. And one mechanism is multi-threading, where the parallelism is exposed by the programmer or compiler at the level of individual threads. Okay. Each thread is essentially an instruction stream. Okay, and it could be having certain amount of state, right? More importantly, it has a program counter which tells which instruction it is being executing, and it might have an associated set of registers where it might be keeping its operands. It could also have what is called a set of local memory locations, right, which are used as private to the thread, right, and various other things, right. The register state is also called as the thread context. We will talk a little bit more about this as we go through the slides, right. And if we're talking about threads from the same processes, then they share the process address space, just like what you could see in a shared memory model. Right. Again, I believe in one of the lectures in the last week, right, people have talked about shared memory programming and distributed memory programming. Right. So in shared memory programming, we have the notion of different processes sharing the address space. Whereas here, when you talk about the threads from the same process, they also share the address space, and you have the notion of a shared memory model. Okay, if you're talking about threads from different programs, of course, they don't share any address space. So the data that they access is private to each of those threads. Right. And when you want to tolerate certain latency, whether it is like a memory latency or a synchronization or the latency of a yeah, a long functional unit, then you have to do a context switch or a thread switch. And a thread switch essentially means that the old thread, that is the current thread which is incurring the stall, right? Its context needs to be saved, and a new thread's context has to be loaded, just like what the operating system does when it is doing a process context switch. Okay, but in the case of an operating system and a process switch, right, one could actually afford to incur certain amount of overhead because the IO delays or the IO stalls is significantly larger, and therefore incurring maybe a few hundreds or maybe even few thousands of cycles. Maybe not few thousands, but maybe let's say up to a few hundreds of cycles, right? Is still okay because you're going to save many more cycles on a process context switch, right? I mean, you're going to save many more cycles by doing a context switch rather. Whereas in the case of multi-threading, you're talking about latencies which are even lower than that, right? For example, you could be doing a context switch to save certain overheads in terms of, let's say, a few tens of cycles, right? In those cases, if your context switch overhead itself is significantly high, then the context switching or the thread switching may not make sense. Therefore, you may want to have enough hardware. We will explain what this hardware is, so that you could actually switch between these different contexts, right, without incurring significant overhead. Or perhaps you want to do context switch at the expense of just a few clock cycles, right? Spending only a few clock cycles, you should be able to do a thread switch. So that is one important difference between thread switching and the traditional process context switching, right? This thread switching has to happen significantly faster, right? Incurring only a few clock cycles. Okay, actually multi-threading was introduced almost like 5 decades ago, right? And the original CDC 6600 machine, which was very popular in the 60s and 70s, that had some notion of multi-threading because there the IO processors were incurring a huge amount of time for doing certain IO processing. And they were actually doing context switching between 10 different IO threads. And what they would do is what is called fixed interleaving. We'll talk about this later on as fine-grained multi-threading, in which in every clock cycle you will switch from one thread to another thread. Right? That's essentially what is called fixed interleaving. Okay, that was there in the original CDC 6600. The idea is very similar to the process switch, right? But you are just switching between different IO threads. In the late 80s or the mid 80s to late 80s, Delacroix proposed what is called the heterogeneous element processor, HEP. And this design had something like 120 threads per processor. And it was able to do a context switch between these different threads, right? And it had up to 8 different processors, each supporting these 120 threads. Okay, it had some very peculiar way of executing instructions, and then the thread switch will happen based on some hardware control. We will not go into the details, but just wanted to give you the perspective that multi-threading was existing or was there right 4-5 decades ago, but even if it's not 5 decades ago, at least 2.5 decades ago, right? 1986 or so is when Denelkar HEP was proposed. Subsequently, in the early 90s, there was a big effort by Burton Smith to build this Tera multi-threaded architecture. This particular architecture had 256 processors, each processor supporting 128 active threads, right? And each thread will essentially, each thread or each instruction in every thread will go through a 21 cycle or a 21 stage processor pipeline, right? And what happens is that in every cycle, you will actually select an instruction from a different thread and you will start executing. That means that if you see this 21 stage pipeline, right, and each one of the stage, there will be an instruction from a different thread, right? So by the time one instruction goes through all the 21 threads, the next instruction from the same thread can actually go after 21 cycles. So essentially within a thread, right, instructions are executed somewhat sequentially, but across threads they were pipelined because the ith instruction and the I+1th instruction from the same thread will execute after 21 cycles, right? Because you're doing a context switch every cycle. That's how the Terra multi-threaded architecture was proposed. Okay, so those are some early multi-threaded processors. We'll also see what is the modern multi-threading, where multi-threading is in modern days. But before we go to that, let's look at what is required to implement multi-threading. This is a simple view from Joel Emmer from MIT of how multi-threading could be supported in a standard instruction execution pipeline. You could see several parts of the instruction execution pipeline, for example, the instruction cache, the instruction register, the arithmetic and logic unit or the functional units, the data cache for doing the memory stage and so on. What has been replicated here is that you could see that the processor register file, general purpose registers, are replicated. Each color corresponds to probably a different thread. So in this particular case, we are talking about 4 different contexts or 4 different register files, which is being shared by 4 different threads. And for each thread, there is a separate program counter because each thread, right, for each thread, one needs to remember which instruction is being currently executed and what is the next instruction to be executed and so on. And this particular processor pipeline essentially chooses between one of these array threads, and then from that particular program counter it is going to fetch the instruction, and it will use the appropriate register file to take the operands from, execute them, and then store the result in the destination register file. If it is a load store operation, then it will perform this using the data cache. The processor pipeline itself is shared among the different threads, and the data cache is also shared among the different threads. That is why they are not explicitly shown here, like which part of the data cache is right for which thread and so on and so forth. Assuming that each one of them would write in the appropriate location, the data cache is shared across all of these threads. Okay, we will actually come back and revisit this notion for different types of multi-threading and what is needed to be done at some high level, okay, little later on. Okay, now let's go a little bit more into the details of multi-threaded processors and then look at how the sharing of resources is going to be done, right? How do multiple threads share the resources of a single processor? It depends on what type of resource it is and whether it has some state associated with it. For example, when you look at things like hardware functional units like the arithmetic and logic unit or the, let's say, floating point multiply units or the integer add units and so on, they don't have any associated state except for certain temporary registers. And these are actually shared by instructions from different threads at different time points, right? They are dynamically shared or they are shared in time, right? Whereas um, certain resources like the processor registers, like the general purpose registers, or even the special purpose registers like the program counter, etc., right? They are replicated one for each context. By replicating this, what happens is that when you want to do a context switch, right, because each thread has its own set of program counter registers and so on, the context is already saved in the hardware. You don't have to save it in memory and then give the registers or the program counter to another thread. That is why thread switching can happen very fast, right? So certain persistent hardware states are replicated one for each thread so that they could actually hold on to their resources even when they are not executing. But important resources like functional units, which are more expensive, quote unquote, more expensive in terms of the amount of space that they occupy in hardware, correct? They are shared across different threads. Now let's look at what happens if I am talking about certain soft states like caches or branch prediction tables and so on and so forth. They are also shared across these different threads, right? Because we know that the address, right? If these are threads from the same process, then they have the notion of a shared address and they may be accessing the same location as well. Therefore, they need to be there. That they need to be there in the cache in only one place so that to provide a consistent view of things, right? Even if they belong to, let's say, two different processes, or even if they correspond to two different locations in the memory, then they're going to occupy two different locations in the cache, maybe two different blocks in the cache, right? And that sharing is anyway going to happen depending on that address, so we don't have to necessarily worry about it. Similarly, when you talk about branch predictors, right, it's going to go based on the program counter address. So either they could be shared or they could be different locations. So they are just shared, right? They are dynamically partitioned. Those structures are dynamically partitioned and shared across these multiple threads. The last one is there are certain states in the processors which are transient, for example, the reorder buffer or the reservation stations, right? And these are also shared across these different threads, and we will show you later on for each implementation how the sharing has to be carefully implemented. Okay, so essentially if you look at it, right, certain resources are time shared between different threads, certain resources are replicated and shared across, replicated, and that's how they do the context switching. And certain other resources like soft states or transient states are either dynamically partitioned or statically partitioned. Statically partitioned means there is a fixed partitioning. Thread 1 can take this part of the ROB, thread 2 can take this part of the ROB, and so on and so forth. We will see how that works later on. Okay. Now the other, yeah, go ahead.
So what happens to the data prefetcher? Like when a processor is switching from one thread to another thread, the data prefetcher might have prefetched instruction for the earlier thread. So it may have to flush all those
It's an
instructions.
instruction prefetcher or a data prefetcher?
So instruction prefetcher.
Okay, instruction prefetch. So it has prefetched the instruction for the other thread, right?
Yes, sir.
Okay. So what's the problem? It can prefetch and keep it. You're going to come back and execute this thread sometime later, right? So all that the prefetching has, multi-threading has had is that it has given you a slightly longer window to do a prefetch. Correct? It's not that because you're doing multi-threading, you're going to abandon the other thread. Correct? The thread for which you have done the prefetch, you're going to come back a little later and execute it. Isn't it?
But the prefetcher size is small, isn't it? I mean, it has to prefetch for other threads also, maybe.
True, true. So there are going to be certain interferences that are going to happen because of multi-threading, right? Whether it is prefetching or even for that matter cache. Normally you expect to exploit spatial locality and temporal locality in caches, right? But when multiple threads share the same cache resource, right, one thread may replace another thread's data. That could happen, correct? So
Yes, sir.
prefetching is nothing but an extension of that. I'm going to talk about the disadvantages, if you want to call it that way, the disadvantages of multi-threading, right? And some of these shared resources like caches and other things are going to suffer because of interference from other threads. Prefetching is a similar case. Does that answer your question?
Yes, sir.
Okay, good. Okay, so let's now talk about the thread scheduling policies. Okay, so the question is, when do you actually do a context switch? When do you do a thread switch from one thread to the other? That depends on what kind of latencies you want to tolerate, right? And we will see actually three different designs, one called coarse multi-threading, coarse grain multi-threading, the other one called fine grain multi-threading, and the third one is called the simultaneous multi-threading. In coarse grain multi-threading, actually the thread switch happens on a specific event, like for a particular latency. If you want to tolerate a certain amount of latency, then you do context switch. Whereas in fine-grained multi-threading, you actually context switch on every cycle, so that you construct your pipeline in such a way, like what I said before. I mean, in the case of Terra, right? It's a 21-stage pipeline, and then instructions from different threads are executed every cycle, so that the I+1th instruction from the same thread is executed after 21 cycles, right? So that's essentially what is fine-grained multi-threading. Simultaneous multi-threading, on the other hand, it's something very different, where you're actually going to pick operations from different threads, pack them together as, right, pack them together as, not so much pack them together, but actually execute them together, let me put it that way, execute them together in the superscalar processor to exploit certain levels of instruction level parallelism. We will see that example also as we go through these slides. Okay, so as I explained, in coarse-grained multi-threading, you do a thread switch whenever the processor is stalled on some event. Okay, and what could these events be? This could be a cache miss, L2 or L3 cache miss. It could be a synchronization event, or it could be a long latency floating point operation. So normally when you execute these instructions in your superscalar, you might be executing these instructions, and then there might be a cache miss. Then there are several cycles on which you stall, and then again you resume your instructions when the when the stalling instruction has been completed. But in the case of a coarse-grained multi-threading, what you do is that once the event that is supposed to trigger the context switch has happened, right? You do a context switch, and then you do start executing, or the processor would start executing instructions from a different thread. So in this case, let's assume that there is a red thread and there is a blue thread. So when the red thread is stalled, you switch to the blue thread and start executing instructions from that. Okay, and in this particular case, in this coarse-grained multi-threading, right, there is a context switch overhead, because the architecture is designed in such a way that certain context is not replicated. Therefore, you do incur maybe 1 or 2 cycles of a context switch. Okay, and what happens is that when the context switch happens, it expects the pipeline to be completely flushed. That is, the instructions which are being executed from, let's say, the red thread has to completely be flushed out of the pipeline before the blue thread can start executing. That's how the pipeline structure is. Okay, so this particular in this particular case, that is in the case of the coarse-grained multi-threading, right, the pipelines are designed to be shorter pipelines, because if you want to flush the pipeline, or if you have to wait for the pipeline flush to happen, if it takes several cycles, then your context switch overhead is going to increase. Okay, that's the point. Okay, so an example of the coarse-grained multi-threading processor is the IBM Northstar processor. Again, if you want to go and look it up, you can do a Google search on that and find out what this processor is all about. Let me show you how the pipeline itself would look like, very similar to what you have seen before, right? The register files are replicated. So there is one register file for the red, and there is another one which is shown as a white color here rather than the blue. And the processor pipelines like the ALU and other things are shared. Some parts of the data cache is also shared between the red and the white thread. Similar case for the instruction cache and branch predictors. And then the thread scheduler, whenever there is an L2 miss, it will switch from one thread to the other thread. So for example, if it is executing the white thread and then there is an L2 miss which has incurred for the white thread, then it will execute the pipeline to be completely flushed from the, means all the instructions from the white thread, right, are completely finished executing in that, right, in the pipeline. And after that, it would start switching to the red thread, start fetching instructions from the red thread and execute them until the red thread incurs a context switch, right? Then it will go and then look whether the white thread has completed its the stalling event has completed, and whether we can start executing additional instructions from the white thread and so on. So this is how coarse-grained multi-threading happens. Whereas in the case of fine-grained multi-threading, you do a context switch every cycle, right? So for example, in the first cycle, you execute instructions from one thread. The next cycle, instructions from the second thread are executed. In the third cycle, instructions from the third thread are executed, and so on. So this is essentially to design a very long or a deep pipeline, and to make sure that data dependencies among these instructions, right, do not incur stalls. Because if I keep switching context every cycle, and if I have enough number of threads as the depth of the pipeline stage, then I don't necessarily incur any data dependency stalls, right? That is where fine-grained multi-threading is useful for, right? So but it requires more number of threads, typically equal to or greater than the number of stages, right? And in fine-grained multi-threading, you essentially favor system throughput as opposed to a single thread performance. For example, if I am going to fetch instructions once every 20 cycles, right, assuming that my pipeline is 20 stages deep, right, then as far as that particular thread is concerned, right, it's as if it's executing sequentially. That means that each instruction is incurring a CPI of 20 cycles, right? So the single thread performance will actually suffer significantly. Whereas you may be executing 20 other threads also together, right? And that performance would be better, or that utilization would be better. Okay. So in the case of fine-grained multi-threading, you have a larger number of contexts, and each context having their own register files, and then you are doing context switch between these different threads. And in this particular case, you are switching between these threads every cycle. Okay, so you are not waiting for any L1 cache miss, or sorry, L2 cache miss or anything. Right? Every cycle the processor switches context and then starts fetching instructions from a different processor.
Excuse me, sir.
Yeah, go ahead.
Sir, won't there be a context switch overhead in this case in fine-grained?
Okay, so in the case of, very good point. So in the case of a fine-grained multi-threading, if there is a context switch, then those are going to be stalls. So the fine-grained multi-threading is designed in such a way that all the threads which are currently active, from which instructions are scheduled, will have all their contexts in the hardware. So there is no context save and restore overhead at all. Okay, and that is why you are able to switch context with zero context switch latency. All right.
Okay, sir.
Okay. So the last case is one of simultaneous multi-threading. And in simultaneous multi-threading, what the processor does is that it essentially, right, takes instructions from whichever thread which is ready, and then it takes all the ready instructions together, and if the superscalar width allows these instructions to be issued and executed, it allows them to be issued and executed. So here what you have is that within each superscalar width and in each cycle, you try to pack as many instructions as possible, or as many operations as possible, from one or more threads. For example, here, right, each white space here is basically no instructions, but a red, blue, yellow, or a green means instructions from one of the 4 threads. So we could see that in some cycles there are some stalls, but then in many of the other cycles there are instructions from different threads which are being packed together, and you are trying to reduce or minimize the number of stalls, right? So here we are actually exploiting the thread level parallelism to improve instruction level parallelism, and therefore effectively use all the processor resources in a better way. Okay, so this is what is called as hyperthreading, okay, which is what is supported in your Intel and AMD processor, right? So Intel and AMD processor says that the number of physical cores is 4, but the number of logical cores is 8. That is because they support hyperthreading, and they try to extract instructions from multiple threads, pack them together, and execute, right? And here again, the resources are shared in a particular way, which I will show you in the next slide. Okay, it has both forms of partitioning, static partitioning, as well as dynamic partitioning, and some of the resources are time shared and some of the resources are space shared. Okay, so one important thing that I want to quickly point out is that the register file which is unordered is actually shared across the different threads. There is no problem, and it can be just shared depending on how many registers are required for each one of them. They need not have to be contiguous. Whereas things like ROB or LSQ, right, which also maintains an ordering information, right, because we know that in ROB the instructions are pushed in the order in which they were fetched and decoded. And you don't want to have instructions from different threads in the ROB in some order, because when one of them is waiting, then it will actually make all of the others also wait. So what happens is that the ROB is partitioned in some way such that consecutive sets of locations, right, is being allocated to one thread, and the other consecutive chunk of location is being allocated to another thread. So again, the partitioning issues are there are certain partitioning issues, and they are carefully dealt with in simultaneous multithreading. In the interest of time, we will not go into those details, but then just wanted to point it out. Okay, now to quickly summarize, right? Typically, we have a superscalar processor, and whenever it incurs a stall, right, those stall cycles are actually experienced and as wasted resources. Whereas in the case of a coarse-grained multi-threading, one could do a context switch and then start executing instructions from another thread, but then you incur certain amount of context switch overhead. Whereas when you go to something like a fine-grained multi-threading, right, every cycle you start fetching instructions from different threads and execute them, but still you would waste some amount of processor cycles or processor slots, I should say, because each of these threads may not have enough parallelism to exploit that superscalar width, right? Therefore, that is why you see many white spaces here, right? For example, this thread has only 3 instructions which could be executed in this particular cycle, and therefore this was wasted. This thread has only 2 instructions that could be executed together, and therefore these 2 are wasted, and so on. Whereas when you talk about simultaneous multi-threading, you try to cover that up by taking instructions from the other threads, right? You pack instructions from different threads to cover your superscalar width. Okay, so as you can see, going from superscalar to coarse-grained multi-threading to fine-grained multi-threading to simultaneous multi-threading, you try to improve the effectiveness of the effectiveness or utilization of the processor resources. Okay, let me just very briefly point out certain design issues in multi-threaded architectures. One is, of course, because there are now multiple threads, each thread requiring their own set of register files, you need a much larger sized register file. And again, soft structures like ROB and load store queues also need to be shared across these different threads, and they have to be they are not replicated, but then in order for different threads to support them meaningfully and not to incur too many stalls, you need slightly larger structures for that. And in the same way, you also need larger structures for other shared resources which store soft states. For example, the cache or your branch predictors or your TLBs, right? Translation look-aside buffers and so on. I mean, technically speaking, you could still deal with the same amount of cache that you had for a single-threaded processor, but then when 4 threads are sharing this same amount of L1 cache, then you are going to have, roughly speaking, only 1/4 of that is going to be allocated for each thread, and therefore you are going to see more misses on this. Somebody pointed out about what happens to prefetching, whether or not there will be interference. There will be interference in almost all of these structures, and therefore, in order to get better performance or in order to have meaningful performance out of multi-threading, some of these structures, their sizes are increased. Even though they may be shared across all of them, they may be increased. Some of them are replicated, and there also the sizes are increased. Okay. Just to summarize again, multi-threading has several advantages in the sense that it has a very inherent way of masking these latencies or tolerating these latencies, thereby improving the utilization of the pipeline. And of course, in simultaneous multi-threading, as we saw, right, instructions from different threads can be used to fill all the slots in a superscalar pipeline and therefore improve the instruction level parallelism, right? The downside of multi-threading is that it always sacrifices single thread performance because the processor resources are now not dedicated to a single thread. It's now dedicated to different threads, and then they are shared in some sense, and that can actually slow down some of these threads. And in implementations such as the coarse-grained multi-threading, right, because after you switch context to a different thread, if that thread keeps running, then the first thread could be starved for a longer durations of time. So one has to talk about fairness issues and how to make sure that each thread has its quantum of execution or whatever. Okay, so that's all about multi-threading in a very quick way. Now, if you ask me, is multi-threading there in modern processors? The answer is yes. Most modern processors do support multi-threading. We already saw that your Intel and AMD processors do some form of hyper-threading. If you talk about the IBM Power 9 processor or the Sun UltraSpark processors like the Niagara processor, they also support up to 4 ways of multi-threading. And Niagara actually supports even a larger number of ways of multi-threading. And more importantly, right, later on you are going to see in these lectures about the graphic processing unit. Right? The graphic processing units also implement some form of multi-threading. In fact, there is this notion of a warp, right, which is basically multiple threads together, 32 threads together. And instructions from these different warps are multi-threaded. Each streaming multiprocessor in a GPU can support up to 32 or 48 active warps, and it can actually do a thread switch or a warp switch between these active warps and keep executing instructions from different warps in different cycles. So there also multi-threading is being employed, right? So multi-threading is a technique which is kind of being exploited in different ways in modern processors. Okay, so with that, what we will do is that we will quickly move to the next part of the talk, which is on multi-cores. Maybe I can just spend 1 or 2 minutes here trying to take questions, right? If
Sir,
there are
I have a
any. Sure.
sir, like how does the processor exactly identify different threads? Like, is it like in a separate memory location, a separate cache or something?
Okay, so I don't know how much you know about pthreads or how much you know about OpenMP and other things, right? So
Yes, sir.
it has to go to that. For example, let us say that if there are these different user threads that are instantiated, so each user thread is going to actually execute a sequence of instructions. They will all be sharing the same instruction cache, but each thread will have its own PC and it will start fetching instructions from those respective program counter locations and start executing. In the case of GPUs, right, these different threads or the different warps are actually executing the same stream of instructions, but they may be executing from different places. Okay.
Okay, sir.
Any other questions?
So in the
Go ahead.
notion of warps, instead of scheduling threads, are we scheduling warps instead? And all the threads inside one warp are sequential.
Okay. Okay. So I probably jumped the gun and talked about GPU. I shouldn't have. Okay. So you can actually think of it in the following way, right? You can think of 32 threads together, right? Put side by side, and then instructions from all of them, right? Together is basically one warp or one warp instruction, right? So every cycle, one warp instruction is executed. Then maybe in the next cycle, an instruction from a different warp can be executed. That's again another 32 instructions together, right? And in the next cycle, again, instruction from a third warp can be executed. Or depending on what the warp scheduler is all about, it can continue to execute instructions from the same warp one after another, which is basically 32 instructions together. And then after that, it can do a context switch when it is supposed to do a switch between one warp to the other warp. Okay, So one way of thinking about it, and until you see how exactly this is happening, it might be slightly confusing. But then just think of 32 threads put one after the other, right, from left to right, and then all of those instructions from all the threads are executed together, and then you go to the next one. This is one warp. Like this, you have multiple sets of warps. Or sorry, like this, you have multiple warps. The instructions from these, each one of them is executed.
Okay.
Okay, I'm sorry if it is not very convincing, but sure enough, I think Madhura or somebody is going to talk about GPUs, where they will actually show you a diagram which will clarify this view.
Yeah, all right.
Okay. Good. Any other questions or any other points? Roughly.
So is the CPU aware of that it is executing different threads,
Yes.
or it just keeps on executing?
It is aware in the sense it has different program counters, right? And it fetches instructions using those things, and then there is this thread scheduler which is a part of the CPU or the processor, which switches this context. So in that sense, it is aware of. But whether it is doing something very different for each thread, answer is no. It's basically for each thread, it's whatever is its PC, it fetches instructions from there and executes it. And when it executes it, it uses the appropriate sets of registers, right? And it does those things. So in that sense, it is aware of the fact that it is executing from different threads. Correct? Because if it is executing, let's say if it is executing from thread 1, and then it has to use the register files corresponding to thread 1. If it is executing from register 2, then it has to execute, it has to take values from register file 2 and so on, isn't it?
Yes.
Yeah. Okay, so let's move on to multi-cores and then maybe come back if you have any more questions on this. Okay. So as we mentioned earlier, thread level parallelism can be supported using hardware multi-threading, where we have replicated only certain resources and then shared the rest of the resources in the pipeline. Right? That's the biggest advantage of multi-threading. Correct? Only things like the register files are replicated, register files and program counters. And maybe we have increased the size of the cache, maybe we have increased the size of the ROB and so on. But then we were able to support, let's say, 2 threads or 4 threads together, right? That was the advantage, and we were able to save many stalls. Whereas when you come to multi-processors or multi-cores, right, the entire processor core is replicated, right? There are multiple cores in a single chip. That is why it is called chip multiprocessing. It is also known as multi-cores. And of course, within each core, you can also support multi-threading. That is also possible. That is what is happening in your current Intel and AMD processors. So in the next 20 minutes or so, we will talk about these multi-cores and how multi-cores can actually execute different threads together. Multi-cores can also support task level parallelism. I think in one of the earlier classes, I think they talked about shared memory systems and distributed memory systems, programming for shared memory systems and distributed memory systems. How do you define a process and how these processes can be executed on these different processors or cores together. So multiprocessors can also execute task level parallelism or a coarse grained parallelism. Okay, so before we go into the details of multi-core processors, let's just try to understand what drove the design of multi-core processors. And of course, all of you know that any innovation that has happened in architecture, right, the credit goes to Moore and Moore's law. And Moore's law essentially stated that the number of transistors in a chip doubles roughly in every 18 months to 2 years. And this trend has been observed for the last 5.5 decades, and it is still continuing, although people say it has slowed down. We will see the reasons for the slowing down also. But in some sense, the number of transistors is essentially doubling every month. Right? This is an exponential growth because you can see that the x-axis, which represents the number of years, is in the linear scale, whereas the y-axis, which is the number of transistors, right, is in log scale. And this is a linear curve in log scale, therefore this is an exponential growth, right? And associated with the increase in the number of transistors, there is an associated performance increase that has also been witnessed, right? I'm sorry. Okay, let me just see. Okay, so let's see that with this increase in the number of transistors, what architectural innovations have happened which has caused improvement in performance, right? Architectural innovations and then the associated performance improvement came because people talked about pipelining. People talked about things like reduced instruction set processors and then speeding up the instruction execution using simple instruction executions and so on. Then subsequently, people also talked about instruction level parallelism processors such as the superscalar processors or the VLIW processors, and that also improved the performance. But these are just architectural innovations where you talk about using these additional number of transistors, how you can support a larger cache, or how you can do some fancy things like branch predictions and so on and so forth, right? But in addition to this, there was also another reason for a performance improvement that was happening. And what was that? Over the years, as newer and newer processors were introduced, they were coming up with faster and faster clock rate, right? The processor clock rates were increasing over the years, right? And this was because of another law called the Dennard scaling, right? As the feature size decreases, right, they found out that the voltage, right, and the current reduces proportionately. Therefore, what you can do is that by decreasing the feature size of the transistors, you can increase the number of transistors, but at the same time operate them faster with lower voltages. That essentially meant that you could have more transistors but then still incur the same power budget. This was all working out very nice, right? And people were able to pack more transistors, and using those increased number of transistors, they could do architectural innovations, come up with newer designs like more complex branch predictors or much larger caches and so on and so forth. And all of them contributed to the performance without increasing the power. And at the same time, the transistors themselves are being faster. That means that what was something like a 1 gigahertz processor a year or year and a half ago has now become like a 1.5 gigahertz processor or a 2 gigahertz processor and so on. And therefore, the cycle time was shrinking, which essentially meant that the execution times were improving. Okay, so that was Dennard scaling. And again, the frequency increase, which was what was implied by the Dennard scaling, was captured in this diagram. Again, as you can see, over the years, right, the processor clock frequency has been steadily increasing. And here again, you can see that the frequency is in log scale. Okay, it's roughly in log scale, right? You can see 100,000 and 10,000. So it's in log scale, right? And these different dots or points here essentially correspond to different processors which were released by various companies, and you can see that the processor clock frequency has been steadily increased, right? They were increasing till about 2005 or so, and after that they seem to have saturated, right? And why did this happen? This happened, right? So before I talk about the saturation, right? So until 2000, right, the processor architectures was riding on this wave of Moore's law and Dennard scaling, where because of the combined effect of this, they were able to get larger number of transistors which were operating faster but requiring the same power budget. So you have all the positives together, right? And therefore, what happened is that the clock frequencies were increasing and users were actually getting more and more performance out of that program without they having to do anything, right? And this is what is called as the free lunch. So programmers did not have to worry about anything. Processors were becoming faster, processors were becoming better, and therefore they were getting much better performance, but at the same time power was not increasing, right? So this is like the best thing that could ever happen, right? That was what was happening pre-2000, right? Post 2000, as you could see, that around 2005 or so, the clock frequency started saturating, right? Why was this happening? This was happening because of the power wall. So what happened is that post 2005, roughly around that time, the Dennard scaling has stopped working. That is because as the feature sizes were decreasing, right, the leakage current is becoming more and more dominant. And when the leakage current is becoming more and more dominant, there are two components to the power part. One is the dynamic current, the other one is the leakage current, right? The dynamic current was the one which was reducing with the feature size, but not the leakage current, right? But the leakage current now started dominating. And because of that, right, as you decrease the feature size, you can increase the number of transistors, but effectively the total leakage current is going to actually increase, and therefore your power budget is also going to increase, right? So that's one reason why Dennard scaling has stopped working, right? And also the feature size decrease is also posing a lot of challenges, and therefore the feature size is not increasing at the same rate as we were expecting it to increase, right, as what was predicted by Moore's law. So it has actually slowed down. It is still increasing, but it has slowed down, right? And these two things combined, the things essentially means that you still have more transistors, but because of Dennard scaling has stopped working, you have higher power, right? And therefore you don't want to operate them at increasing clock frequencies, because that will again blow up your power budget. Remember that the power dissipated is proportional to frequency, and an associated thing is the voltage also. Actually power is proportional to voltage square and frequency, therefore you will have a cubic effect of that. Okay. So what we have post 2000 is that you have more transistors but operating at the same speed. This is the way by which you can keep the power budget intact. Okay. So the frequencies are flattening, and now what do we do with this increased number of transistors? One thing that we can do is that you could actually build deeper superscalar processors, but then the amount of instruction level parallelism that can be exploited is limited. Therefore, as you build more complex superscalar processors, your returns are going to be diminishing. You're not going to get much gain out of that, right? So what architects did was that they started building multiple cores. That is what that drove multiple cores, right? The following slide essentially explains it. People were expecting the clock frequencies to keep increasing, but this wasn't happening because around 2005 or so, right, the processor designers have to met with power wall, right? And blocked by power wall, they just turned right and then started increasing the number of cores per processors. So one of the earliest multi-core processors was the IBM Power Processor, which had two processor cores. And as you can see in this diagram, right, each one of this red rectangle represent one of the cores, right? It's actually the core part of the core. There is something else which is the Shad L2 cache, which is also shared across the two cores, that is shown at the bottom of the diagram. But this is one of the earliest multi-core architectures having two cores, right? Subsequently, Intel also followed the suite, and they also had something like a 2-core processor, and then later on a 4-core processor or a 8-core processors. Today, you also talk about 16 cores, 32 cores, or 64 cores. Essentially, what's happening here is that each processor socket, or each processor, so to say, has multiple cores, and each core in itself has the complete set of pipelines, your superscalar architecture, plus your L1, L2 cache, and so on and so forth. Plus, in addition to these cores, there is also some level of a shared L3 cache which is shared across all of these cores, and other structures like the queue, IO units, the memory controllers, and so on and so forth. And then if you have a shared cache, then there is some kind of a connectivity from the different cores to the shared cache and so on, right? So that's essentially what is your multi-core architecture. So your multi-core architecture has multiple processors, where each processor has a complete processor pipeline, plus the register files, plus its own L1, L2 caches, plus the uncore part, which is essentially the shared L3 cache, the memory controllers, which is connecting to the DRAM, right? And the interconnects, which is basically connecting the cores to the L3 cache and the memory controller, plus other accelerators like crypto accelerator or media accelerator, which might also form a part of the uncore architecture. You're not going to see any of these details of these cores or uncores. The cores, of course, we have already seen they are basically superscalar processors, now replicated, right? Now let's see how these different cores are connected to the shared L3 cache, or how these different cores talk to each other, right? For that, you essentially build some kind of an interconnect network, right? And this interconnect network is characterized by the interconnect topology. And the simplest interconnect topology is the shared bus. And on the shared bus, all of these processor cores, right, are tied to. So you could see that there are different processor cores, and each of these processor core has its own L1 and L2 cache, which are what are called as the private caches, right? And all of these cores are now tied to the shared bus, to which the shared last level cache is also tied to. So any of these processors want to access the shared last level cache can actually send a request through the shared bus and then access the last level cache. If the data is there in the last level cache, then it can be fetched. If the data is not there in the last level cache, maybe the request is sent to the memory controllers, and then from the memory controller it will fetch from the DRAM and then bring it to the cache. The advantage of the bus interconnect is that it's the simplest interconnect structure, but the disadvantage is, of course, that it's a shared media and only one of them can access the bus at any given time. So if you have a larger number of cores, typically more than 4 or something like that, then there is a lot of contention on the bus. As opposed to bus, one could actually build what is called a crossbar kind of a network, where each processor can be talking to any of the banks. So now here the LLC is banked as multiple banks, and then the memory controller is another device. So each one of these cores can be connected to any of these banks or the memory controller by means of this crossbar network. And the crossbar network essentially makes connection between a processor and a core by means through a switch, right? So depending on which of these switches is connected, that particular processor will be talking to the specific bank. And here the notion of the idea is something very similar to your networking ideas, right? But here you have a crossbar switch, a crossbar of switches. Okay, there are also other kinds of interconnects like the ring network, which is similar to the bus network, except that the ends are connected to each other. But this is a point-to-point network in the sense that if a processor wants to talk to a particular memory bank, then it has to route its message through these many switches, and then it has to come to that particular bank. Similarly, if this processor wants to talk to this bank, then it has to route the message through these controllers and switches, and then it has to come to that particular bank. Okay, so ring is another kind of a topology which also exists, and some of the earlier Intel processors, right, like the Sandy Bridge processors, use the ring topology. Then, of course, one could talk about what is called the mesh topology, right, where again these processors and banks, right, are now connected by means of a 3x3 mesh here. As you can see, there's a 3x3 mesh. There are 3x3 9 switches, and each one of these device or core is essentially connected to one of the switches. And here you can talk about the XY kind of a routing. So for example, if this core wants to talk to, let us say, this particular bank, then the data can be routed through this switch, through this switch, through this switch, and then to the switch. So in a mesh network, right, you will have to pass through a number of hops before the message can go to the destination network, right? Okay, if time permits, I will come back to this diagram and talk about something else, but for the time being, let's just leave that. There is also another network called torus network, which is similar to the mesh network, where the ends are connected with each other. I have not shown that yet. Let me take the last 5 minutes and then quickly talk about shared memory architectures and distributed memory architectures. And even in shared memory architecture, let me talk about what is called the centralized shared memory and the distributed shared memory. And later on, I will also relate them to the multi-core architecture. In the case of a centralized shared memory architecture, there are these different processors, right? And these processors are connected to one or more of the memory modules. But the memory modules are across a interconnect network. Therefore, irrespective of which memory module a processor is trying to access, the latency is going to be the same because it has to go through the interconnect network to that particular memory module, right? Therefore, this essentially presents what is called a uniform memory access architecture. That means that irrespective of which memory module the processor is accessing, the latency is likely to be uniform because it has to go through the interconnect network. As opposed to this, in the case of a distributed shared memory architecture, right, we have a processor and a memory together, and that is connected to an interconnect network. So if this processor wants to access a memory location which is from this memory, then it is going to be faster because it is local to the processor. Whereas if this processor wants to access a memory location which is over here, then it is slower because it is across the network. So in this particular case, we have the notion of what is called a non-uniform memory access architecture. Right? I only talked about memory here, I didn't talk about cache, but the processor can actually cache the data from the remote location and store it in its private cache, which can happen both in the case of the centralized shared memory architecture as well as in the non-uniform memory or the distributed shared memory architecture. But both of them support the notion of shared memory. That means that the memory is shared across all of these processors, and any processor can access any of the memory locations. There is a hardware abstraction which is implementing this, right? As opposed to this, later on we will talk about what is called a distributed memory architecture, where the memory is not shared, or what is also called as the message passing architecture. But before we go to that, let's just look at how multi-cores, right, essentially implement either a shared memory, centralized shared memory architecture or a distributed shared memory architecture, right? So, sorry. So if you take a server system with a single processor or a single socket, which may be containing something like, let's say, 4 cores, then that represents a centralized shared memory. Because in that particular processor, there are 4 cores, and then each core may have 1 or more levels of private memory, and then some level of shared memory. But then any of these cores will actually see the processor's memory across this memory controller, and the time it takes to access the memory is uniform across all the cores or uniform to any of these memory locations. Therefore, this is essentially called the uniform memory access architecture, where you have, right, a server board with a single socket. Now let's look at a server board with 2 sockets, right? If you are looking at a server board with 2 sockets, each socket having 4 cores, right, and every core having its own private memory and some level of shared memory as well. But the processors or the processors are connected by means of this quick path interconnects. This is in the case of the Intel processor. So I'm sorry. So when the processor cores wants to access this memory, right, then the latency is something where it has to traverse through this interconnect network, go to this memory controller and access the memory. But if the processor cores want to access certain memory locations which are in this memory, then it has to traverse through the interconnect network, go to the quick path interconnect, and then traverse to the other socket, go to the memory controller, and then access the data. That's much slower, right? Similarly for cores over here, if they want to access the memory location in this memory, it's faster. But if they want to access the memory over here, then it has to go through the quick path interconnect. So this is the case of what is called a distributed shared memory architecture, or what is called a non-uniform memory access architecture. Okay, let me take 2 more minutes and then quickly complete. If you're talking about the distributed memory architecture, which is where the memory is not shared, then essentially you have the processor and memory, but then they are connected by means of the network, but the processor 1 here cannot access the memory of the other processor, right? But they have to communicate by means of explicit messages. So here each one of these processors is what are called processor nodes, and they are connected by an interconnect network. This is what is your cluster architecture. How do you build your cluster architecture? For example, if you take your server node, which may have 1 or more sockets, right? The quick path interconnects, or the interconnect connects through the PCI bus, through the IO hub and the PCI bus to a network interconnect, right? And these different network interconnects can be connected to a network switch, and that forms a distributed memory architecture. So here we have essentially 4 nodes, right? And each of these nodes have its own memory, right? And any core in one node cannot access the memory of another node, but within it they can access the memory, right? So that's essentially a distributed memory architecture. That's how clusters are actually built. Okay, now let me just put this last slide here and then leave it so that when Madhu comes later today, he will talk about cache coherence. So let me just leave with this one last slide, right? Where again, if you're looking at either a centralized shared memory or a distributed shared memory, what we saw is that the memory is on the other side of the interconnect network, right? And therefore, the cores have their own private caches, and they may cache some of the locations into their private caches. So this is going to cause this notion of what is called a cache coherence problem, which is what is going to be discussed in the next lecture. The cache coherence problem happens because of your private caches, right? Because of your L1, L2 caches in this example. Because what is being cached in L3, there is no problem, because, right, every other core is going to see exactly the same value. But the moment you go to a distributed shared memory architecture, right, where now your L3 cache has become private, right, for this set of cores or for this set of cores, then even the data which is stored in L3 could become stale because of the cache coherence problem, which is what is going to be discussed in the next lecture. Okay, so with that, I will kind of conclude my lectures on multi-cores and multi-threading, right? Maybe I have taken 2 extra minutes and stop here. If it is okay, we can take questions. Otherwise, we will leave the floor for the next lecture. Thank you.
Sir, one question.
Okay.
So why cannot an architecture have something like memory-to-memory communication? As DRAM chips have an embedded processor inside that, so why couldn't that be implemented?
DRAMs have embedded processors inside that? Not DIMMs. Not DIMMs.
Like
If you're
processing in
talking
memory,
about processor in memory, that is something different, but that is meant for something else. So if you look at your DIMMs, right? The DIMMs are, what should I say? They are really dumb devices. They store values, and somebody has to tell them to get the value out of it. They can't do anything more than that, right? See, as you can see here, right, memory is basically storage, right? I believe, I think there were some lectures on memory as well, right? How memory is organized and so on, right? And the memory controller is the one which basically gives all the commands to read the memory. Correct? The DIMMs otherwise is like a passive device. Correct? And the memory controllers can actually talk to each other and then make sure that they get the data. And that in some sense is what is happening, but then the memory controllers talk through the QPI in this particular example. Okay?
Yes.
Okay, I think I should stop here because I think Professor Madhu is waiting for the next lecture. So let me unshare my slides. Thank you so much. Thanks, Madhura, for hosting me.
Thank you, sir.
Thank you. Bye.